Okay, then what will happen when we have more than two predictors? I mean, if the output y follow this linear function beta 0 plus beta 1 times x1, the first predictor, beta 2 times second predictor, up to p number of predictor plus irreducible error, observation noise, epsilon. Okay, everything is the same except few considerations. Okay, again, how to learn, how to find coefficient beta 0 to beta p for this multivariate linear regression task. We have to define RSS function. RSS function is again a function of coefficient, function of beta 0 to beta p. This is sum over all your training data point residual squares, yi minus beta 0 minus beta 1 x1 minus beta p xp square. Oh, sorry, here we have to indicate the training data point index. So let's say xip indicate the ith data point p's input predictor. Okay. And how to find the coefficient? Just solve this optimization problem. Minimize with respect to this coefficient with the objective function RSS. Right. So among the p number of predictor, essentially, to improve the performance, we have to consider correlations among predictors. Essentially, it is nice to increase the number of parameters or increase the number of predictors when you just care about the training error. If you just want to minimize the training error, you have to increase the number of predictors. You have to increase the number of parameters. But training error is not important thing. Our really goal is to minimize the test error, right? When it comes to test error, it is not good idea to increase the coefficient as many as possible. This is not good idea. When you increase the coefficient or degree of freedom, you also increase the chance of overfitting. We will discuss overfitting many times throughout this course, and we will go more deeper in chapter 5 and 6. Anyway, so we have to control the number of coefficient very carefully. This is very important thing, and this is actually the main part in our course, right? So why I say this? Among p predictor, there might be something irrelevant to your output, or there might be something that is redundant to your output prediction. Let's consider this simple, interesting example. When there's very beautiful beach and there are many ice cream vendors. But one interesting situation always we can observe, when ice cream sales increases, we always observe more shock attack. So the more ice cream, the more shock attack. So from this, you might think, okay, to reduce the shock attack, we have to ban ice cream. Is it a good idea? No. That is absolutely nonsense. Indeed, there is hidden factor, temperature. Indeed, temperature is more related factor to shock attack. So indeed, temperature increase cause ice cream sales increase. The temperature increase also cause shock attack increase. Right. So this is more important. So when we let x1 denote ice cream and x2 denote temperature, and let's say there are two input predictor and the number of shock attack is y, we can design linear regression model with two input predictor. One is for ice cream cake, ice cream sales. One is for temperature, like this. So we define RSS function with respect to these three parameter or coefficient beta 0, beta 1, beta 2, and then find the nice beta 0, beta 1, beta 2 by minimizing the RSS function. Then you might see very nice training error. But here, the ice cream sales, the x1, is kind of redundant thing. When temperature is given, the sales of ice cream information is totally useless when the temperature is given. So in terms of test error, including these factors, beta 1 times x1 is not a good idea. It is better to remove beta 1 x1 to improve test error. Right? So when you have a multiple input predictor, that is not always good. You have to very carefully consider how can you choose very relevant input predictors. That is one best way to improve your very important test error rather than training error. Okay. So in chapter 5 and chapter 6, we will very much study these things, how to choose the nice model, how to choose the input predictors among many other things. Right. Maybe in lecture note and lecture videos, you can see some method called forward selection and backward selection. What is the idea? So forward selection and backward selection pretty much same. The only difference thing is forward selection start from the empty predictors and the backward selection start from the full predictors. Okay, so the first selection, first train at the first step, first train the model beta 0, just a constant model, and then see the RSS value. Second page, add one more predictor, then you can have p different model, and each model contain only one single predictor. And then train each model using parameter beta 0 and beta 1. Maybe each model will converge to different coefficient beta 0 and beta 1, and compare them and pick the best one among p different models. Let's say this is the best input predictor. Second phase, since you have x2 from the previous step, you still have p minus 1 remaining input predictor. So what should we do next? We just add remaining predictors one by one. So here, x1, x3, x4, and so on. And then train each model and see RSS value. Let's say this is the best. Okay. So as you proceed this force selection search process, you will observe better training error, better RSS values as you increase the number of predictors. Always, as you increase more predictors, as you increase the number of parameters, as you increase the degree of freedom, you can observe improved training error. Okay, that is rule of thumb. But again, we don't want to minimize training error. We want to minimize test error. So decreasing test error, not always good news. Decreasing training error can make generalization error or the variational error, which cannot be observed from your training data point. Okay, so we have to estimate the test error from your training data point. So in chapter 5 and chapter 6, we will discuss how to find the best model, how to find the best number of predictors, how to estimate the test error for each model. That is very important. But please wait until chapter 5 and chapter 6.